Welcome to the video on activities. Alright, so now we can adjust the thermodynamic expressions that we've discussed earlier in earlier videos for the deviations that we see in our discussion of phase diagrams. So we can now introduce the concept of activity in order to adjust our treatment of ideal solutions for actual real solutions that we see in the real world. So here we have a table of standard states. This is from Atkins. This is table 5.3. So you can see that for various components, solids or liquids, for solvents and for solutes, we have various standard states. For solids or liquids, the standard state is pure. The activity there is 1. For a solvent, we're looking at Raoult's law. The standard state is the pure solvent, and the activity there is related to the vapor pressure. So the activity is equal to the vapor pressure that we actually see divided by the vapor pressure of the pure solvent, and we're then going to derive a few other things here. And then we'll then also look at, for a solute, our basis is going to be Henry's law, and we can then talk about two different standard states, a hypothetical state of a pure solute, or a hypothetical state of the solute at some molality B known here. Alright, so remember that the chemical potential of a solvent A is given by this equation. So chemical potential of A is equal to the chemical potential of A when it's pure, so not mixed yet, plus R times T times the natural log of the vapor pressure of A in the solution divided by the vapor pressure of A while it's pure, so the PA star. Remember the star there means that we have a pure substance, so either here or there, that star means the same thing, that A is pure. Alright, so remember that for an ideal solution, our solvent is obeying Raoult's law. Raoult's law is given here, so the vapor pressure of A above the solution is equal to the mole fraction of A in the solution times the vapor pressure of A when it's pure. And this means that now we can replace that fraction that we had earlier. So now we can get the the chemical potential of A is equal to the chemical potential of A when it's pure, plus R times T times the natural log of the mole fraction of A in our solution. And we can preserve the form of this equation even if our solvent isn't obeying Raoult's law by just replacing chi there, the mole fraction of A, with A of A, the activity of A, right? So activity is the lowercase a, and then the subscript A is denoting which species we have. So our activity, again, can be thought of sort of as an effective mole fraction of A. And this means that our effective mole fraction, our activity of A, is equal to the vapor pressure of A in the solution divided by the vapor pressure of A if it's pure. And this means that to find the activity of a solvent is pretty easy, because all we have to do is measure the vapor pressure of our solvent in solution and compare that to our pure solvent. If we have a dilute solution of our solute, then the vapor pressure of A, the solvent, the mole fraction is pretty close to 1. The activity will also be pretty close to 1 because the vapor pressure will be pretty close to the pure vapor pressure. So all solvents obey Raoult's law more and more closely as the solvent concentration approaches 0, as we get more and more dilute of our solute and a larger and larger mole fraction of our solvent. And this means that our activity approaches our mole fraction as the mole fraction approaches 1. So that means that the activity of A is approaching the mole fraction of A as the mole fraction of A is approaching 1. And now we can introduce then our activity coefficient, gamma, that we define this way. So the activity of A is equal to our activity coefficient, gamma of A, times the mole fraction of A. And this means that because, as we saw here, because the activity of A trends towards the mole fraction of A as the mole fraction goes to 1, that means that gamma must go to 1, gamma of A must go to 1 as the mole fraction of A goes to 1. So as our solvent is getting more and more pure, our solution is getting more and more dilute, our gamma is getting closer and closer to 1, our solution is acting more and more, our solvent is acting more and more like an ideal solution. And so this means that our chemical potential of our solvent can then be given with this formula. So now we have the chemical potential of A in the solution is equal to the chemical potential of A while it's pure plus R times T times the natural log of the mole fraction of A in our solution plus R times T times the natural log of gamma of A, our activity coefficient. And this means that when our mole fraction is 1, our solvent is pure, the activity is 1, and thus our effective mole fraction is equal to our mole fraction. And note that in that case, then the natural log of 1 is 0. So here we have the natural log of 0. So, the natural log of 1, which is 0. So this term goes away if we have a mole fraction of 1. And if we have a mole fraction of 1, then gamma also goes to 1. That means that this term goes away. And that means that when A is pure, the chemical potential of A is equal to the chemical potential of A when it's pure. That's not terribly surprising. Right, so the activity of solutes approaches the ideal dilute behavior, so Henry's law behavior, as our mole fraction of our solute, chi B, is approaching 0, not 1 as it was for the solute. And so let's first examine a solute that obeys Henry's law, and then let's examine the repercussions of some deviations from Henry's law. Right, so for a solute B that follows Henry's law, it has a vapor pressure that's given by this. Remember, Henry's law looks really similar to Raoult's law, except we're changing the vapor pressure of pure B to be this Kb, right? This experimental, this empirical constant that we find. And so now the chemical potential of B, we get an equation that looks something like this. So the chemical potential of B in the mixture is equal to the chemical potential of B while it's pure plus R times T times the natural log of the vapor pressure of B divided by the vapor pressure of pure B. And now we can then use Henry's law to get rid of this vapor pressure of B. So now we get the chemical potential of B is equal to the chemical potential of pure B plus R times T times the natural log of our Henry's law constant Kb divided by the vapor pressure of pure B plus R times T times the natural log of the mole fraction of B. Now, both Kb and Pb star are characteristics of our solute, so these can be combined together to get a new standard chemical potential with B as a dilute solute. So note that now we have mu B naught, where the naught is now saying that B is our dilute solute, and so we're wrapping together sort of this chemical potential of B when it's pure and this Kb over Pb star term. And that means that now we can simplify our chemical potential of B to be our mu B naught term plus R times T times the natural log of chi B, the mole fraction of B. And if the solution is ideal, then that means that Kb is equal to the vapor pressure of B when it's pure. And that means that then that mu B naught is equal to mu B star. So, now let's consider deviations from Henry's law. So if our solute doesn't obey Henry's law, so let's introduce the activity of our solute. So this is AB. And now we get the chemical potential of B is equal to chemical potential of B naught plus R times T times the natural log of our activity of B. And now, this means that now all of our deviations from ideality are wrapped up all in this activity of B term, right? And everything else is not a deviation from ideality at all. It's all wrapped up here in the activity. And so now our activity can be determined by the Wave pressure of B divided by Kb, and our experimentally determined Henry's law constant. And now we can introduce our activity coefficient. So the activity of B is equal to the activity coefficient gamma B times our mole fraction of B, chi B. And now, remember before, all of our deviations from ideality were wrapped up into our activity A. Well, now we have them all wrapped up into our activity coefficient, gamma. Right? So they're now all wrapped up in there. And now, our solute is obeying Henry's law as its concentration approaches 0, which means that the activity of B approaches the mole fraction of B, and gamma B approaches 1 as our mole fraction goes to 0. Right? Note that this is differing from our solvent because now it's as the mole fraction goes to 0 instead of with the solvent the mole fraction approaching 1. So this is true at all temperatures and pressures, and this means that any deviations of our solute from ideality are disappearing as our solute concentration gets closer and closer to 0. So as our solute is getting more and more dilute, it's acting more and more ideal. Alright, so remember that our selection of a standard state is entirely arbitrary. We could choose whichever value we want, and so we choose a standard state that's convenient, usually. And a lot of times it's more convenient to work with molalities instead of mole fraction. And this means that now we can change our chemical potential term. So we get chemical potential of B is equal to chemical potential of B naught. Where note that this mu B naught has a different value than the earlier mu B naught did, plus RT times natural log of B, so where B here is the molality of our species B. Right? So in this case, our chemical potential of our solute has its standard value, mu B naught, when the molality of B is equal to B naught, which we generally mean as 1 mol/mol, 1 mole per kilogram. And note that as the molality approaches 0, then the chemical potential approaches infinity. And this means that as the solute becomes more dilute, it becomes more and more and more stable. So as a result, it becomes increasingly difficult to remove the last traces of a solute from solution. So do we really have pure water ever? Not really, because it becomes harder and harder and harder to distill or deionize the water. Right? So at some point we go, it's good enough. We'll work with it that way. So just bear in mind that we don't ever really get pure stuff. And so we can incorporate deviations from ideality by introducing the activity of our solute, AB, and the dimensionless activity coefficient, gamma B. And so now the activity of B is equal to gamma B, our activity coefficient, times the molality of B divided by the standard molality of B, 1 mol. So where then our gamma term is approaching 1 as the molality approaches 0. And again, this is valid at all temperatures and pressures. And just like before, our deviation from ideality is captured entirely in our activity coefficient, this gamma B. Right? So all of our deviations from idealities are occurring here in this one term. Right? That is very nice for us. We want to wrap all of these deviations all together. All right. So now, if we incorporate our activity into our earlier equation, that now gives us mu B equals mu B naught plus RT times natural log of our activity of B. And because we're free to choose any arbitrary standard state, we can choose a convenient standard state for biological applications. We don't have to use a standard state of 1 mol, because really in biological systems, 1 mol is really, really concentrated. So the conventional standard state of hydrogen ions is an activity of 1, which again is corresponding to a pH of 0, because we have a molarity of 1 molar. But this is impractical for biological systems, so usually we use a biological standard state in which the pH is equal to 7, so an activity of 10 to the minus 7. And now we label our standard thermodynamic functions like this, so we have this sort of G naught plus, H naught plus, S naught plus, and mu naught plus. So, now our chemical potential of a hydrogen ion then becomes chemical potential of hydrogen ion is equal to chemical potential of hydrogen ion naught. So at standard state, plus R times T times the natural log of the activity of the hydrogen ion. And this guy, this term, R times T times the natural log of the activity, well, that simplifies to R times T times the natural log of 10 times the pH. Because remember, the pH is minus log base 10 of the hydrogen ion concentration. And so we can then make this simplification here. And this means that now we can relate our thermodynamic and biological standard states using this equation. And so now at 298K, 7RT natural log of 10 has this value of 39.96 kilojoules per mole. So it's around 40 kilojoules per mole. So that means that our biological standard state differs from our thermodynamic standard state by roughly 40 kilojoules per mole. And so from our earlier discussion of regular solutions, remember that we have this sort of equation. We've got our Gibbs energy of mixing is equal to N times R times T times the mole fraction of A times the natural log of the mole fraction of A plus the mole fraction of B times the natural log of the mole fraction of B plus our dimensionless quantity xi times the mole fraction of A times the mole fraction of B. And we can show that this equation implies then, if you want to see the math, look at the Atkins book. So that then implies that the natural log of gamma A, remember gamma is our activity coefficient, is equal to xi times the mole fraction of B squared. Note that this is B here and A there. And then we have sort of a similar term, so the natural log of gamma B is equal to xi times chi A squared. So then I have up here. So these are called the Margol's equations, and we can use these Margol's equations to write the activity of A. So the activity of A is equal to gamma A times mole fraction of A, which is equal to the mole fraction of A times E to the xi chi B squared, which is equal to mole fraction of A to E to the power of xi times 1 minus mole fraction of A quantity squared. And remember that the activity of A is also the ratio of the vapor pressure of A in solution to the vapor pressure of pure A. That's what we have here. And that means that now we can write this equation. So if we put that function again here. Now this function is plotted to the right. So here we have the ratio between the vapor pressure of A to the vapor pressure of A when it's pure, so PA over PA star, as a function of mole fraction of A. So if xi is equal to 0, then that means that we have an ideal solution, and that means that our curve is a straight line, just like it should be for Raoult's law. But if we have positive values, so up here, positive values of xi, this is for endothermic mixing due to unfavorable solute-solvent interactions. These give us vapor pressures that are higher than ideal, because it's easier to separate the solute and the solvent because of that, we've already basically put in some of that energy of separating the molecules by putting in the solute. And then negative values of Xi. So this is for exothermic mixing. So this is due to favorable solute-solvent interactions. These are vapor pressures lower than ideal because it's harder to remove. Now we have even more intermolecular forces than we did just with the pure solvent. So we have a lower vapor pressure than we do ideally. So all these curves approach in linearity up here as the mole fraction of A reaches 1. So they're approaching linearity. They're approaching Raoult's law as we get closer to a mole fraction of A. So as we get a more dilute solution here. Right, so if the mole fraction of A is much less than 1, this box should be a much less than sign. So if the mole fraction of A is much less than 1, then that means that we can say that the vapor pressure of A is equal to chi A, the mole fraction of A, times the E to the xi, times the vapor pressure of A while it's pure. And this equation has a form that looks something like Henry's law. If the Henry's law constant Ka is equal to E to the xi times the vapor pressure of A while it's pure, Pa star. And so the interactions between ions in solution are so strong that our approximations here of replacing the activities with molalities is only valid at really, really low concentrations, so really dilute solutions, so less than 1 millimole per kilogram of total ion concentration. So only if the total ion concentration out of all the ions that you have present is less than 1 millimolal. So that means that really we need to be using our activities and not the molalities. All right, so the chemical potential of the cation M plus is we're going to write as mu plus, and the chemical potential of our anion X minus we're going to write mu minus, just to keep the notation in check a little bit. And our Gibbs energy, our molar Gibbs energy Gm of our ions in an electrically neutral solution. That's the sum of these partial molar quantities. So that means that now the ideal molar Gibbs energy is equal to the ideal chemical potential of our cation plus the ideal chemical potential of our anion. But this means that for a real solution, we really have the molar Gibbs energy is equal to the real chemical potential of our cation plus the real chemical potential of our anion. Well, each of those can get separated out into two terms. One term that is our chemical potential ideally, and one term that is the deviation from ideality. That's RT times the natural log of our activity coefficient. So in this case, the activity coefficient of our cation, and in this case, the activity coefficient of our anion. And then we can combine together these two RT natural log terms. And so now our actual real Gibbs energy is equal to the ideal Gibbs energy, molar Gibbs energy, plus R times T times the natural log of the product between our two activity coefficients for our cation and anion. And so now, note that all of our deviations from ideality are again captured only by this last term, right? And really, those aren't deviations at all. It's all just here in these two gamma terms. And so we can't experimentally separate our the product of the two activity coefficients because we can't separate and have just a solution of cations and just a solution of anions. We have to keep them mixed. So we can only assume that that non-ideality arises equally from each kind of ion, both the cations and the anions, and this means that we have to introduce our mean activity coefficients. Right? So this is mean activity coefficient gamma plus minus as a geometric mean of our individual activity coefficients. So that means that gamma plus minus is equal to the square root of gamma plus times gamma minus. And now we can express our individual chemical potentials of our ions. So chemical potential of the cation is equal to the chemical potential of the cation if it's ideal plus R times T times the natural log of gamma plus minus. And a similar term for for our anion. And now we can generalize this sort of approach for a compound with ions of an arbitrary charge. So MpXQ, that dissolves to give P cations and Q anions. So we're getting the P and Q are coefficients here. Well, they're the subscripts in our compound here. Those are the numbers of cations and anions that we get out of each formula unit of our compound. So now our molar Gibbs energy of our ions is the sum of the partial molar Gibbs energies, which in other words is their chemical potentials. So now the molar Gibbs energy is equal to P times mu plus Q times mu minus. Well, that's equal to the ideal molar Gibbs energy plus P times R times T times the natural log of gamma plus Q times R times T times the natural log of gamma minus. And again, now if we introduce our mean activity coefficient in a more general way than the last time with where we had charges of just plus and minus 1. So that means that now gamma plus minus is equal to gamma plus to the power of P times gamma minus to the power of Q, all to the power 1 over S. So we're taking the S root, right, where S is the sum of P and Q. So in the last case, we had a P of 1 and a Q of 1, so each one was to a power of 1, so it wasn't shown. And S was 2, then because we had 1 plus 1. But if we have something like, so that would have been for a case like sodium chloride. But if we have something like magnesium chloride, well, in that case, P is 1 and Q is 2, so then S would be 3. So then we're taking the cube root of this product here. Alright, so now we can write our chemical potential of each ion like this. So now we can say that the chemical potential of ion I is equal to the chemical potential of ion I if it's ideal plus R times T times the natural log of gamma plus minus. Alright, now, this brings us to the Debye-Hückel Limiting Law. So, Coulombic interactions between ions are long range. So these are electrostatic interactions. So they're likely to be primary contributions to the deviation from ideality in our ionic solutions. This is the major component of our deviations from ideality. And so this is going to be the basis for our Debye-Hückel theory of ionic solutions that was developed by Peter Debye and Erich Hückel. Now, the mathematical calculation here involved is beyond the scope of this course, so we're not really going to get into it. Well, we're not going to get into it at all, but we're going to examine the theory sort of qualitatively and what it means for us. And so, oppositely charged ions will attract one another, and this means that, as a result, anions are likely to be clustered near cations, and cations are likely to be clustered near anions. So if we have here, say, we've got two types of ions. We've got blue ions, and we've got the red ions. Now, it doesn't matter which one we call which. Let's call the blue ones cations and the red ones anions. Doesn't matter. So if we look at any one particular cation, it's surrounded by anions, like nearby. Farther away, of course, there are some other cations and then also some other anions around as well. But within a sphere of relatively small radius, so this sort of darker sphere here, the counterions are significantly more common than the like-charged ions, and this means that this sphere is representing the sphere containing over time the charge of the same magnitude but opposite sign of the charge on the central ion. So if we have sodium chloride, it will contain over time one of the opposite ion, right, on average. And so, but if we have something like if the blue one there is our cation, so if we have sodium, then over time our gray circle here contains one chloride ion. But if we have magnesium chloride, then over time our gray circle here encapsulates two chloride ions. Right, so this sphere, this gray sphere, is what we call the ionic atmosphere. So the energy and thus the chemical potential of our given central ion is lowered as a result of its electrostatic interactions with its ionic atmosphere. Right? It's more stable for that cation to be in that charged ionic atmosphere of opposite charge. And this lowering of energy is the difference between the molar Gibbs energy, Gm, and the ideal value, Gm ideal, of our solute. And this energy difference is given by RT times the natural log of gamma plus minus. And at low solute concentrations, this energy difference is small, because at low concentrations, gamma tends towards 1, so then we have the natural log of 1, and that means that the whole term is trending towards 0. So at low concentrations, the activity coefficient can be calculated from the Debye-Hückel Limiting Law, which is given here. So the log of gamma plus minus is equal to minus the absolute value of the product of our charges, Z plus and Z minus, times A, where A is 0.509 for aqueous solutions at 25 degrees C, times I to the power of 1/2, so square root of I, where I here is our dimensionless ionic strength of our solution given by this formula, so I is equal to 1/2 times the sum over all of our ions I of the charge of the ion squared, times Bi, so that's the molality of that ion, divided by our standard molality B0, so that's 1 molal, remember. So that is the same equation here. So Zi is the charge of our ion, Bi is our molality, B0 is our standard molality of 1 molal, and this sum goes over all of our ions present in solution, not just the ions of 1 formula unit or of 1 compound. So for a solution with only one type of cation and one type of anion, so as long as it's just a 2-component sort of system, 2 compounds, one of our solvent and one of our solute, that may be composed of ions. That means that then I is equal to 1/2 of B plus times Z plus squared plus B minus times Z minus squared, all divided by B0. So this means that our ionic strength emphasizes the charges of our ions because the charge here is squared, so the Z minus and the Z plus is squared. So the ionic strength for a variety of ion pairs is shown here. So if we have a cation with a charge of 1 and an anion with a charge of 1, the ionic strength is 1. But if we have a cation with a charge of 2 and an anion with a charge of 1, the ionic strength is 3. And of course you see that it goes up. And so if we get a cation with a charge of 4 and an anion with a charge of 3, then the ionic strength is 42. Note that it goes back down if we get to like charges. So if we have a cation with a charge of 4 and an anion with a charge of 4, it goes back down to 16 because now you don't have, you have a stoichiometric ratio between the two, right? So it's a 1-to-1 mixture. And so you also note that along this sort of curve, this line, 1, 4, 9, 16, those are all perfect squares. Those are all slightly lower than the values around them. So this term limiting law in the Debye-Hückel Limiting Law is applied because our ionic solutions of moderate molalities can have activity coefficients that differ from the values that we predict by the law. But all of our solutions are obeying the law as the molality approaches 0. Right? So in the limit of 0, the law works. All solutions obey it. Right? There are no solutions that don't obey the Debye-Hückel Limiting Law in the limit of the molality approaching 0. And so over here, we've got a table. Again, this is from Atkins. This is table 5.5. This table gives the activity coefficients as a function of molality. And so as we increase the molality, the activity coefficient for potassium chloride is dropping. The activity coefficient for calcium chloride is dropping. Note that at a very dilute solution of potassium chloride, the activity coefficient is pretty close to 1. But as the molality gets closer to 1 molal, that activity coefficient is dropping off pretty significantly. So this figure is showing then the dependence of the activity coefficient on ionic strength. And so note that down here we have 100 times the ionic strength, or rather the square root of ionic strength. And on this side we have log of gamma plus minus, so the activity coefficient. So as we increase the ionic strength, our activity coefficient is getting lower, or rather the logarithm of our activity coefficient is getting lower. So that means that while there are significant deviations at moderate concentrations, so over here, this means that the values predicted by the Debye-Hückel Limiting Law will apply pretty well down here at low concentrations. Right? At high concentrations there are significant deviations, but down here the Debye-Hückel Limiting Law works pretty darn well. So when the Debye-Hückel Limiting Law fails at moderate ionic strength, then the coefficient can be estimated from the extended Debye-Hückel Law, which is given here. And note here that this B and C are dimensionless constants, and furthermore, B can be interpreted as a measure of the closest approach of the ions, so how close together they get at their closest, but it's sort of best regarded as an adjustable empirical parameter, and C is also best regarded as an adjustable empirical parameter. So we have to just go out and measure these things. So upon comparing the limiting law, so the dotted line here, that's this line here, and the extended law, which is the solid line, so that's this line there, is shown here. And note that the extended law works reasonably well compared to our data points, even at moderate concentrations over here. It still fails at high concentrations. So at concentrations higher than that, it'll still fail. So as long as our concentration is below about 0.1 molal, it works. But note that that's better than the Debye-Hückel limiting law, which worked only up until about 0.1 millimolal. So that was activities.